Hi everyone, in this video I'm going to do the solutions to the two examples of logarithmic differentiation. Alright, so first thing, this is a typo. There should be logarithmic differentiation to find dy dx. So the instructions say to give dy dx as an explicit function of x only. That extra sentence just means make sure at the end you solve for dy dx and then swap out the y at the end. So if you follow the steps that are in the notes, you'll have answered these questions. All right, so first what I want to do is actually look at the first page of notes in this section, because this x to the x example, so these are the steps written out, and then this x to the x example right here, this is going to be your roadmap for all of these problems. They'll all kind of use these same couple of steps. So I want to take a minute and kind of walk through this example together. So your first step will always be to ln both sides. So if this equals that, then the ln of this equals the ln of that. And then you're going to use the log rule that brings the exponent down out front. So I'm not taking anybody's derivative or doing anything else here. I'm just taking this down. And in fact, taking advantage of this log rule is why we have ln'd both sides. We wanted to introduce some kind of logarithm so that we could bring that down, because it removes kind of like the biggest problem in our derivative. So this x comes down, and then from here, it's just an implicit differentiation problem. So ln of y, ln's derivative is 1 over x, so we got 1 over y dy dx. On the right-hand side, we use the product rule. Then to solve for dy dx, you multiply both sides by y, just to get rid of this 1 over y. So I have y times the whole right-hand side. Make sure you always include this big set of parentheses. Otherwise, you would just have y on the first term, which isn't quite what you mean. So in this class, all the examples that we do will start with y equals some expression of x here, which means that your left-hand side is always going to look like this. So you'll always have ln of y here, 1 over y dy dx, and then that same algebra step here. So it's weird, but it'll at least be consistent. All right, so the only reason we don't stop here is because y was originally given as a function of x, so it's polite to give its derivative as a function of x as well. So instead of leaving y here, we use this original relationship, and we just plug in x to the x instead of y. So we just put x to the x in that spot times the same stuff, and we're good to go. So it's a lot of steps to remember, but always come back to this x to the x example and use it as your roadmap, because the steps will be really consistent. The only thing that'll really change is kind of what you're dealing with in your product rule here, and kind of what these derivatives end up being. All right, so now we'll focus on our examples. Our first one is 2x plus 1 raised to the x power. Okay, so the first step in x to the x was ln both sides, so that's what we'll do here. If this equals that, then the ln of this equals the ln of that. And then we say, oh look, I have an exponent inside of a log, so I see I can bring this x down out front using the power rule from the log rules section. So I'll bring that x down. So I just have 2x plus 1 without an exponent left inside that ln. Now I say, oh yeah, okay, now I can take the derivative of both sides here. That's no problem. So what I'm going to do is take the derivative, and I put d dx at the side just to remind myself in this step that's what I actually did. I'm about to take the derivative with respect to x on both sides. So the derivative of ln of y is the exact same as it was in that last example, 1 over y dy dx. And on the right-hand side, we have a product rule again. Because they're multiplied together, I can tell I'm going to need the product rule. So my f would be x, my g is the ln of 2x plus 1. F prime is 1, because that's the derivative of x. For g prime, we're actually going to need the chain rule. So the outside function in the chain rule would be the ln. The inside is that 2x plus 1. The derivative of ln of x is 1 over x, and then g prime would be 2. So for g prime here, oh, I should use the red. For g prime here, we'll have f prime of g times g prime. And you can put that 2 kind of as the numerator there, or just kind of leave it as it is. All right, so I'll take my red f and g information and use the product rule on it. So I have f times g prime plus g times f prime. And of course, you could do some cleanup if you wanted to. I probably won't bother except for just not writing this times 1 because it doesn't make a difference. All right, so we want to solve for dy dx, and it'll be that same single step from the x to the x example. Just multiply both sides times y, and that gets rid of the 1 over y here. So dy dx equals y times all that stuff. And I'll skip the times 1. So now the very, very last step is replace that y with the original expression of y here, so that you have dy dx as a function of just x. So in my original line, y was 2x plus 1 to the x. So I'll put that instead of y, and then everything else will stay the same. Again, I could clean up the term I'm writing right now, but I'm not going to bother. All right, and that last line right here is my final answer. Okay, so from here, I'm going to use those exact same steps to do the second example. If you'd like to cut to the final answer, feel free to fast forward, but I'll just keep walking through it. All right, so we'll start this one just like we started the last one, which is ln both sides. That's where we'll always start. The next step is to use the log rule that brings the exponent down. So now our exponent is log of x, so that whole thing comes down out front, just as a log rule. So I haven't taken anybody's derivative yet. So log of x is out front. Now I just have ln of plain x here. And what I have on the right-hand side is kind of weird. I have a log base 10 times a log base e. That derivative is going to be fun. But at least now we're in shape to actually do the derivative. So I'm going to ddx both sides, and you may realize that left-hand side is doing exactly the same thing again. So the derivative of ln of y will be 1 over y dy dx for the same reason that it was in the last two. On the right-hand side, I have a product rule again. And I'm going to be really careful about this just because those two logs together are kind of weird. So my f is log of x, remember that's base 10, and my g is ln of x, that's base e. All right, so we know the derivative of ln of x is 1 over x. That's a really nice one. For log of x, I'm going to peek back to my new derivative rule for logarithms. We would have 1 over x times the ln of the base, and this is secretly base 10, so we have 1 over x ln 10. And realize that's actually what we did here. This is 1 over x ln e, but then ln e is 1, so it kind of disappears, so we have a shortcut. All right, so we're going to use these red pieces in the product rule for this right-hand side here. So I have f times g prime plus g times f prime. Okay. So now I want to multiply both sides by y to solve for dy dx again. Dy dx equals y, and then a big set of parentheses, just that whole right-hand side. And of course, our final step is the same as the final step in the last two, which is instead of y, we're going to plug in the original expression, x to the log of x in this case. So my final answer is dy dx equals x to the log of x times all that same stuff. And as always, if you have the urge to clean this up and simplify a little bit, you're welcome to, but it's not really required. That is my final answer. That was fun.